Remind you guys, so again, Andre, you heard the news, but again, want to remind you, this class had some good news. AP cut units 8, 9, and 10 from this class and from the AP test. So what that means is we now, crazily, have, is that a word? Crazily?
Yeah.
Sure, we'll go with it. We only have 2 units to do this semester. We're starting unit 6, which is Simple Harmonic Motion. And then we're going to do, the next unit is 7, Torque and Rotational Motion. And that's it. That's the only new material that we got to cover this semester. We don't have to do 8, 9, and 10. So that leaves us basically with a bunch of time. I'm pretty sure if I go even a little bit slow,
What are we done by?
I was going to say, I thought it was like beginning of March we'd be done. So we would have March and April with nothing to do. Well, we do, but no new content. Basically just puts us in a really good position. We definitely need to take advantage of that and not waste it, right? Because you guys still have your AP test on May 5th. It's still going to be tough. It's still going to be a challenge. That's the whole point of that test. So we need to use it. It just gives us more time to be preparing, reviewing, doing practice tests, things like that. So we're in a really good position. Today what I want to do is I want to get started on Unit 6. Again, Unit 6 is Simple Harmonic Motion. We're going to talk about what that is, define it, and then also start to talk about some of the introductory concepts for this unit. It's kind of a unique one. And then Unit 7, what we'll do later, is torque and rotational motion, which I gave you a preview. Torque is just a twisting force. So that makes sense that if you apply a twisting force to something, you create rotational motion. That's all about Unit 7. That's what it'll be. So for today, I'm going to dive in and get started on Unit 6, introducing some of these main concepts, and then a loose plan for kind of see how far we can get. Nice notes packet that I didn't make, to be fair. I found kind of a nice summary of all the key equations and things that we're going to talk about. So I'm going to give you guys that as a kind of extra help for summarizing what we talked about. I want it to supplement or add to the notes you're taking. Right? A lot of you don't seem to take notes, which I guess to do school however you want, but I really encourage it, right? And want you to be at least aware and following with me as I'm going through this stuff, right? I don't want you to just sit in this room for an hour and a half and say you learned about Simple Harmonic. I want you to be engaged, ask me questions, right? You guys are fairly quiet, and that.
It could be loud.
No. In terms of engagement or asking me questions or answering my questions, I really encourage you guys to get involved and stop me if something doesn't make sense. Even if it's something little, I don't care. I want to clarify that and make sure we're all on the same page. When I'm asking for thoughts, just give me your thoughts. I don't care about right or wrong. I don't want you to be caring about if you're right or wrong. We're just introducing stuff. If you knew it all right away, then why are you taking this class? I want to know what your initial thoughts are so we can figure out okay, we're thinking about it differently, we got to switch, things like that. So this is some sort of a summary of kind of our goals, I guess. Defining simple harmonic motion, and then recognizing if a situation is truly simple harmonic motion or if it's something slightly different. There's a kind of specific, nuanced definition for SHM. You'll see that abbreviation a lot for what that is. So be able to recognize, this situation, this is simple harmonic motion. Or this one, no, it's not. There's something missing, and here's why. These are a lot of vocab words, right? You might know some of them, right? Angle makes sense, position. Some of them you might not know, like what's an amplitude. Centripetal acceleration we've seen. frequency you might have heard, but maybe don't know the physics meaning. That's okay. There's a lot of new terms with this unit. We'll talk about those. I want to connect simple harmonic motion to circular motion, right? There's a lot of crossover. They're not the same thing, but there's a lot of overlap between the two, and I want to show you how they do overlap. And then also, the final goal is to be able to use all these terms and predict and calculate and solve all these different things for a sample problem that's simple harmonic motion. Right? We'll build up to calculating position, velocity, figuring out acceleration at any point in the motion, things like that. So this is just in a nutshell kind of objectives. You want me to wait a sec? I'll let you guys jot those down. Yeah, and you really don't need to write all these if you don't want to. We'll talk about them. I'll define all of these words. If you want to get the main, you could talk about distinguish different variables in simple harmonic motion. This one, you can jot down if you want to. This slide is kind of a preview of what we're going to talk about, some main goals, or at least main concepts that we're going to work towards. So while some of you guys are still writing up, I want to take a second. Again, I want thoughts. I don't care if they're right or wrong. What would you guess simple harmonic motion is? What would you guess would be, say, a definition to simple harmonic motion? Any thoughts? Just holler at them. Anything. Please, give me something. You have to have thoughts about this. I want to know where you're at. What do you think this means?
Maybe two motions that are in sync with each other.
Okay, I like it. Two motions in sync, right? I'm guessing you're touching on the harmonic piece, right? We talked a little bit about that harmony. Things are in harmony. They're working together. They're in sync. That's a great one, right?
Something in circular motion working with something flat. How do they
Ooh, okay.
get together?
So circular motion and linear motion kind of in sync with each other? Is that what you were saying?
Yeah,
or?
to create the motion of a circle moving motion.
Okay, I like that. Any other thoughts? Again, we're just diving in. I don't expect you to know this at all. I was just curious what your thoughts are. This is the technical definition, right? This is... Feel free to write this down. It's a little lengthy, but at least jot it down. Simple harmonic motion is something very specific. Motion in which a body or an object moves back and forth over a fixed path. It doesn't change its path. It does the same path back and forth. It returns to each position, velocity, and acceleration after a certain interval of time. Right? This is the full definition of, in physics, what we would define simple harmonic motion as. Again, it's talking about motion of an object. It's repetitive. Do you see the back and forth? It's a repetitive motion that repeats itself. There's a fixed path. Right? It doesn't repeat itself changing directions or repeat itself in a new location. The path is set and it repeats itself over that same path over and over and over. And it's very routine and predictable, right? After a definite interval of time, a known amount of time, it will return to either the same position that it started with, or at these 2 points in time, after say 1 second has passed, the velocity will be the same. And another second later, the velocity will be the same, right? Or at certain points in time, after certain intervals, the acceleration is the same. At 0 seconds, at 2 seconds, at 4 seconds, at 6 seconds, the acceleration is the same at each of those times. There's a specific interval where these variables repeat themselves. That should make a lot of sense, because it just said it's the motion that goes back and forth. It repeats itself in a specific path. Well, go figure. After a certain amount of time, it will go back to where it started.
It's like sound waves, because like sound waves are like they start and stop at the same spot.
Bingo.
That's where the harmonic comes.
A sine wave, you know what a sine wave is, a cosine wave? It's literally a function that is a wave. It goes up and down, up and down, up and down. That is an example of simple harmonic motion. There's a certain period of time where it repeats itself, and at each of those time intervals, it will come back to the same place, or it'll come back to the same velocity. It's a great example, and that's like the mathematical or fundamental concept that underlies simple harmonic motion. Any simple harmonic motion you'll be able to graph or model using sine or cosine waves. Right? The math and science are very much intertwined, and that's a situation where you can't separate the two. The motion is defined by the mathematical wave. But in a nutshell, I want you to take, at this point, it's repeated motion, goes back and forth, it's rhythmic, routine, it's got a specific path, and there's specific time intervals when these variables repeat themselves. It goes over and over and over. Is that my door?
Yeah.
Who's there?
Hi there.
Evan's been referred to real quick.
Yes. Evan, interview. I guess I'm assuming if that's okay with you. You should have asked.
I get it.
Alright, so are we good with the general idea of simple harmonic motion? We feeling okay? Ethan?
So this has to do with circular motion in some way, right?
Yes, there's a relationship to it, yes.
Isn't there some... Shoot, I learned about this a long time ago. There's this thing with where if you put a point inside of a circle and let the circle move, the inside of the circle will be there, like where that point is along
creates
the
a
circle.
sine wave.
Yeah.
Yes. Yeah. I'll try and find a seeing a visual of that is super helpful. It's hard to think about it. But yes, you're right. Later on, remind me if I don't mention it, but I will show you there is a definite connection between circular motion and a harmonic motion. In that specific example. That's a good point.
Does it have to be, like, back and forth between like one point to the other, or something where it'll go down and down and up?
Yes. Yeah, that still works, right? Your wave could dip, 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 and then dip, 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 right? The simple harmonic motion is only limited by it's a back and forth or repeated motion over a certain path.
Okay.
So you're right. It doesn't have to be just a wave, right? It could be stair step, stair step, stair step, right? All sorts of things that a simple harmonic motion could be. This is a classic example of a simple harmonic motion, right? This is a spring, I don't know what the... Technically, you could call it a spring pendulum. It's not a traditional swinging pendulum, but it's a back and forth using spring. Do you see the characteristics of a simple harmonic motion in this motion?
Mm-hmm.
Right? Back and forth. That was a key concept for simple harmonic. It's back and forth. Right? It's two springs, things going back and forth. Does that make sense? There's a fixed path. This thing isn't changing its path. It's staying in the same position, going back and forth. It's not turning directions. It's not moving. It's moving in a specific path back and forth. Do you see the rhythm of it, like the harmonic aspect? Right? It stops, then zips fast, and then slows down and stops, then zips and goes back. Right? That harmonic piece, right? Think about, let's look at position. Do you see there's a certain amount of time? It starts here, takes a certain amount of time, and gets back to that same position. Right? It's the same every single time. If you look at this position in the center, 1 1,000, 2 1,000, 3 seconds, 1 1,000, 2 1,000, 3 1,000. Right? There's a definite time interval when it returns to that position. Do you also see kind of the velocity? Velocity 0 at that moment. Velocity 0. 0. 0. Right? Those position, velocity, and acceleration, the values of those variables are also rhythmic or repeated. Right? So you kind of see that, right? What we're really going to dive into is calculating that. What is the position here? What is the acceleration here? What's the velocity right in the middle? Right? We're going to be able to calculate all those, find equations that describe this motion. All right? This is another one. This, I'm almost positive, is a particle model of a sound wave. Right? Well, this would be a standing sound wave, like a sound wave inside a tube or something. When you, again, we're not going to get to talk about this. This is Unit 10. Sounds kind of cool. When you speak or make noise, there's like pressure of the particles that builds and then pushes the particles in front of it, which pushes the particles in front of it. That's how sound's transmitted. That's why you don't have sound in outer space. Yeah, you have no air particles to transmit sound waves. Right? They can't go anywhere. But this is, it's better to think about this like a standing wave in a pool. Right? You know a wave pool? They make a wave and keeps it constant. The particles go back and forth as the wave flows. Right? Do you see how the particle motion, the physical motion, is matched by a sine wave? Right? If you turn this on its side, that's waves going like this. Simple harmonic motion. It's back and forth. It's a certain path. It's rhythmic. Right? That's another example. Here's a really good one. Inside your engine. Right? In a nutshell, combustion engines in cars, they have gas explosions that push a cylinder or piston up, and they keep doing that over and over. As they move up, they rotate what's called the crankshaft that basically spins and then eventually spins the wheels in your car. In a very, very nutshell, that's how your engines work. This is definitely simple harmonic motion, right? If you watch that piston, goes back and forth. Back and forth. It's a fixed path. It's going along the same path every single time. And it's rhythmic, right? It hits the bottom of, well, it doesn't actually, but it hits the bottom of the cylinder. After a certain amount of time, it returns that position over and over in a definite path. Hits the top in a definite path. All these are just showing you examples of simple harmonic motion. This is a really weird one. This is actually very poor 3D rendering of, say, like an ant or, huh? Stick bug, right? Or this could be like a robot that's mimicking like an insect. But do you see the simple harmonic motion? Like if you watch one leg, forward, backward, it doesn't change speeds. It's rhythmic, it's steady. It's the same path over and over. And you combine basically a bunch of independent rhythms or simple harmonic motions to produce the walking of this bug. All of these are just showing you examples. Here's an interesting one. The movie Dumbo. This one scene shows you, what is this? Pendulum, right? A pendulum is simple harmonic motion. Should make sense when you apply the definition of simple harmonic motion to the motion of a pendulum. It's a definite path. It's back and forth. Literally the definition of a pendulum. Or when you're swinging on a swing, right? Assuming that you're swinging steady, back and forth, back and forth. The same path, it's rhythmic, right? Here's another kind of crazy one. This is a 3D function.
It's like a water drop, right?
Yes. I don't actually know where this is a 3D model. I'm pretty sure it is modeling like a droplet being dropped onto like the surface of calm water, right? It blips and creates a wave. The wave flows out, but it's rhythmic. It's uniform. Now this one technically is not back and forth, but the way this is simple harmonic motion is you drop in a set, every half a second. You release a drop, so you can repeat this over and over. That is what makes it simple harmonic, because it's repetitive, because technically those waves disperse, but if you repeat the drop, it creates that wave over and over. Ethan, this is very similar to your question. Can you create circular motion and make a wave out of it? It's very similar to what this is. I don't know if this is supposed to model anything, but does this remind you guys of anything in real life that you've seen that's common? Specifically the blue ball moving along the...
Clock?
Huh?
Kind of like a clock?
Similar, yeah, it's rotating just like a clock.
It's going the opposite direction of the clock.
Huh?
It's going counterclockwise.
Right, but yeah. Roller coaster. I have something specific in my mind that I think of right away.
That's higher.
Hey, Mr. Marsh.
Thank you.
Are those mine?
Yeah, I know why I have two of them. There you go.
Oh, well, there's one I didn't have a cap for. Thank you. All right, so if I say it, it should ring a bell. A train.
Oh, yes.
Oh.
You see it? Right? That's how trains work. They have the bar that connects one point on all the wheels, and it goes like this as the train wheels move forward. Right? You move that bar in the same motion, right?
So upset.
I know.
So upset.
That was a bad teacher question. Teachers shouldn't fish for a certain answer. They should look for one answer and kind of lead you towards it. But in this situation, there's that was one specific thing that's spot on. But a train engine, right? I don't know. Does anybody know train terms or anything? That bar that connects all the wheels, that bar rotates as the wheel rotates. That's combining linear motion, two linear motions. That bar goes back and forth and up and down, but it results in circular motion that turns the wheels.
Circular or is it more than oval? What is that like?
It should be circular, right? If you had an oval wheel on a train track, it'd go clump, 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 clump.
But the motion though, because it's not like it's going out and then I don't know.
If it's a perfect square, then it'll be a circle.
Okay, yeah, I guess it's just.
If it's going up and down and left and right.
Yeah, and I guess I'm comparing the bar's motion up and down to a point on that bar and circle, right? When you link circular motion with linear motion and you allow movement, that they kind of overlap. That's partially what I'm talking about. Anyway, I just wanted to show you that was more or less kind of showing you a bunch of good examples to kind of get in your head for, wait a minute, what's simple harmonic motion look like? I should give you a bunch of examples to define them. This is review. There's a reason I'm reviewing this now. There's a big connection to simple harmonic motion. Remember Hooke's law? The force of springs. Does anybody remember the equation? Well, this is Hooke's law for the force. Does anybody remember the equation for the energy stored in a spring?
But you
Wasn't it like 1/2 K times M?
Close. 1/2 K. What variable do you have to change the compression of the spring?
Oh, wait.
X, right? How much you squish it. So 1/2 kx squared. So if you actually measured it, we measured the force versus the distance that we're compressing. The force and compression is linear, right? The more I push the spring, the more force it pushes back on me. Or if I increment, I need the same amount of force to squish 1 centimeter, 1 centimeter. It's linear, and the slope of that line is k. This is literally y equals mx plus b. Well, there's no y-intercept. It's at 0. The slope of the line is k. Here's my x variable. Here's my y variable. Right? Does anybody remember what the area under the curve for force versus distance was? The hint is force times distance.
Yeah.
What physics quantity do you get when you multiply the force?
Oh,
Not quite.
right, the work.
Oh man.
The work not good.
Does work ring a bell? Work is if you apply a force over a certain distance, you do work. If you find the area underneath the curve of force distance, well, all you're doing is finding the area, which is length times width, force times distance. Force times distance is the definition of work. You can average it out, right? It's a slope. You could do 1/2 base times height, or you could average it out, and they're the same. Force times distance. So your work becomes this equation, 1/2 kx times x, right? That was for the spring energy. And there's the potential energy for a spring. Does that make sense? Okay. Just so that you understand the algebra here, you can average this triangle to a rectangle. What is this height? Well, it's force. The force is kx. Kx is my height. X is my length. Right? But I have a triangle. I got to cut it in half. That's where the algebra comes from. The reason I want to go over that is because that will become very important in the equations that we're going to use for simple harmonic motion. Okay? This is going to be fairly tricky for you guys, but you're aided in, I'm showing you or plotting the force, the position, the velocity, and the acceleration at any moment in time. So kind of watch it for a few cycles and think about, like, okay, what happens if I get all the way to the end? Well, the velocity disappeared right there. The position is maximum, at least away from the center point. Where is the acceleration maximum? There and there. That's where the acceleration vector is largest. So go through one by one. Where is the force the greatest?
At the ends.
At the ends. You guys see that? When it hits the very end, the force vector is largest. Where is the velocity the largest? The velocity is this purple arrow.
Right in the middle.
In the middle. Good. In the middle of the motion, it's moving the fastest. What about acceleration? On the ends. Here's a good one. When is the force and the acceleration in the same direction? And when is the force and acceleration in the opposite direction?
They're the same.
Good. This is a trick question. You get why? Is there ever going to be a time when the force of motion is a different direction than the acceleration of the motion? No, because force causes acceleration. When you apply it, the spring force pulls it back to its natural state, equilibrium. That force direction is trying to accelerate. So there's never a change or a time when they're in opposite directions. When are they in the same direction? It's another slightly trick question. All the time. Right? F equals ma. M is a scalar. So if you have F, force and acceleration, they have to be in the same direction. They have to be equal in direction. How about velocity and acceleration? When are velocity and acceleration in the same direction?
Immediately after it stops.
Yeah. Ethan's saying immediately after it stops moving, like right there. Do you see that? The velocity will flip right there. And then as soon as it passes the midpoint, now they're opposite. Yep. They're opposite. Now they're together. Opposite. Together. Opposite. Together. Opposite. Together. Right? That's another unique thing about a spring pendulum. Why are they in the same direction? Why is it that on this direction they're the same?
Because it's always trying to go back to the center. The acceleration is bringing it to the center.
Yep.
And it's going towards it.
And it overshoots, basically.
Right.
It builds up a bunch of speed, but it overshoots the midpoint. Well, the only way it can stop is when the spring gets stretched and it tugs it back to the center. It'll overshoot again. Right? It's the same when it's trying to return it to the middle. Once it overshoots the middle, your acceleration is slowing it down. It slows it down, pulls it back, then slows it down, pulls it back. All right? This is a really useful graphic that shows a lot of information. Right? This kind of makes sense. We see it's obviously simple harmonic motion. Do you see these definite intervals of time when the force is the same? Right? The force is largest there, there, there. Right? The position is maximum at the ends. At the end. At the end. It changes direction, but the size of the displacement, this is my 0 point. The maximum displacement is over here or over there. They're equal and opposite. Okay? I'm going to skip the energy for now. I'm going to come back to it. I want to talk about these. So these, if you're taking notes, this is key things that I want you to write down. These are new vocab words. The period of simple harmonic motion is described by a capital T. The period of motion is defined as the time it takes to make one complete cycle. That's really important to know. The period of simple harmonic motion, capital T, it is the time it takes for that object in motion to make a full cycle. Right? If we're looking at that spring, if it starts on one end, a full cycle would be it goes all the way to the other end and then back. That's one cycle. If you record how long that takes, that is your period of the motion. It's super important. The literal opposite, or specifically inverse of period, is what's called frequency. Frequency, you should know what that means, right? How often something happens. What's the frequency of going to school? Well, it's every day in a row for 5 days. What's the frequency of the sun rising? Every 24 hours, give or take. Right? Frequency is how often something happens. In this situation, how many cycles happen every second? Right? 2 cycles every second is the frequency. Have you ever heard the term hertz?
It's a frequency.
It's a frequency. The term hertz, it tells you how many cycles happen in a given second. You guys probably know your internet, right? Wi-Fi. You guys seen 2.4 gigahertz and 5 gigahertz? Those are two different frequencies of a signal that your Wi-Fi router sends out. A giga is 10 to the 9th, if I'm not confusing them. So 2.4 gigahertz means that every second, 2.4 times 10 to the 9th waves occur. That's a lot. The wave of your Wi-Fi is incredibly fast every single second. 5 gigahertz is even more. There's more complete cycles that happen in 1 second. That's what a frequency is. How many complete cycles happen per second? It's more or less the speed. It's a very loose physics term, but essentially it's the speed of the wave or repeated motion.
So it's like your internet's like 5G, that's what it's talking about?
Yes.
Okay.
Well, I don't know if this, I think cell phone data works the same. I think 5G means a 5 gigahertz signal, but I'm not 100% sure. I'm pretty sure it is. But even 5G, it might technically be closer to like 6 gigahertz. I don't know. Please don't quote me on that.
But that's what the G is supposed to represent, right? When they're talking about that?
I think so.
I mean, I know, like, obviously things aren't like perfect. Like when they say like a TV is 70 inches, might be a 70-inch glass, but it could be like 79.
Yeah, I just don't know 100%, so don't quote me. Maybe one of us can look that up and clarify next class. But anyway, the last term that I want to talk about really is amplitude. Has anybody heard of this or have a guess of what amplitude means? Or have you used it in other contexts? Amplitude, in a nutshell, is the size, right? The maximum displacement from equilibrium, right? So on that spring pendulum, this is your equilibrium point, right in the middle when that spring's at rest. The amplitude, is this. From equilibrium to the maximum distance away, that is the amplitude. This is also the amplitude. It's rhythmic, it goes to two directions, but either side you pick, the maximum distance from the 0 point, it's the same. One's in the positive x direction, one's in the negative x. Amplitude is the maximum distance away from your equilibrium position.
So 2A will always be the most.
Yes, correct. If you have simple harmonic motion, and it goes from one end to another, and the amplitude from your 0 point to one extreme end is A, even saying 2A would be the maximum length of the total motion. And that's correct. Because simple harmonic motion is rhythmic and routine. It's not going to change. If you want to think about units, period is always the amount of time per one cycle. It's always this way, so you could even tell me technically that the period is 5 seconds. You wouldn't have to technically say 5 seconds per one cycle, because a period by definition is the time of one cycle. So I could tell you the period is 5 seconds, and you understand that's 5 seconds for a complete cycle. Frequency is very similar. How many cycles per second? Oftentimes, you'll see frequencies written as just 1 over seconds, right? Basically, not unitless over seconds. There's this implied understanding that frequency is how many cycles or completions or whatever, rotations per second. That's implied. So sometimes if you see 50 1 over seconds, that's hertz. 50 cycles per second. There's this kind of, I don't know where it comes from, to be honest with you. Technically it's cycles per second, but sometimes you could see 1 over seconds. Or the problem will say 50 hertz. You have to realize, okay, hertz is cycles per second, so it's 50 cycles per second. Hertz is one of those terms or units we made up I think it's somebody's name. They figured it out. Here's another relationship. Do you see how period is seconds per cycle? And frequency is cycles per second? They're literally flipped from each other. This is really important. This is really important to understand because a lot of questions, they'll tell you the period, but the equation you need is the frequency. And you're going to read the question like, it doesn't tell me the frequency. How am I supposed to solve this? This is what you're going to have to understand. You can find the frequency by taking inverse of the period. Then you know the frequency and you can move on with the equation you want to solve the problem. This is really common to have to flip back and forth. So I really want you to understand these are inverse of each other. Okay? And then amplitude, it's a distance. How far from the midpoint to its maximum distance or displacement. We measure that in meters. Meters is our standard unit for length for science classes and specifically the SI units. Meters, seconds, newtons, all those things. Oops. So I want you to practice this. Right? We have a mass pendulum. You can obviously see it's simple harmonic motion. It's got back and forth, repeated motion on a definite path. This line is marking the equilibrium point. If you'd stop that spring and let it hang where it wants to, balanced, it would be that point from the bottom of that cube. So I want you to, I'm going to try and do this. The clock in the top right, once I click it, the clock will go. I'm going to try and start the clock exactly when it crosses that line. So I'll do it when it's coming down. 1, 2, 3, 4, 5. Do you agree with me? That's kind of how long it took. 1, 2 seconds, 3 seconds, 4 seconds. And it's back to where it started. It did one complete down and back. Right? So if it takes 5 seconds to do one complete cycle, which of these can you answer right away? To complete one cycle, it took 5 seconds. The period. Period is the time it takes to do one cycle. Can you find the frequency using the period? Yeah. Do the inverse. If 5 seconds per cycle was the period, flip it. Do 1 divided by 5. What would that be? 0.2, 1/5. What are the units? Hertz or cycles per second. And then, okay, how about the amplitude? This is a little trickier. There's this kind of giant ruler they add. I'm going to try to mark it right about there. Oh, wait. Right here. At this line. It's, 4.9 centimeters on the ruler is the maximum, and that's from measuring from up here. So I need to find, okay, what's the lowest distance on the ruler? It's like 8.7, something like that. Yeah, 8.7. So how do I find the amplitude if I know the maximum distance and the minimum distance? Be careful that you recall what the definition of amplitude was. Can anybody tell me what was amplitude?
The measurement
The distance, it's the
displacement.
max distance from equilibrium.
From equilibrium. Maximum distance from the midpoint, the 0 point. This was our equilibrium position. This was the system at rest. It wants to be here. So how do I figure out half of the distance if I got the beginning and ending? The max height was what, 8.7? The minimum height was 4.9. Don't I want to find half of that? Because this is an amplitude, and that's an amplitude. Yeah, I want to find the difference. So in this case, I'm subtracting and divide by 2. I have no idea what that comes out to be. Yep, so they got the same thing. 8.7 was this position. 4.9 was the minimum position. Right? Amplitude is half of the total, like, displacement. I want to know from midpoint to one end. So I take half of it. So the amplitude is approximately 1.9 centimeters. Remember, amplitude is a distance or displacement. And boom, we figured this out. Takes 5 seconds for a complete cycle. 1 over that is the frequency. Right? So this is something where you might not be given a graphic like this, but you might be given a wave. And you got to say, like, hey, how long does it take to make one complete cycle? That would be the period. So I'd go, okay, that is one cycle. What's the time period? Frequency is opposite or inverse. And the amplitude is from mid-neutral point or equilibrium point to, in one direction, the maximum. Oh. It says my battery's going to die. What time do we... 45?
55.
Yes, you can. 5%. Yeah, I'll try and throw the ant out. Oh, it's going to die. I really don't want it to because I got a recording and I would be pissed if it lost my recording. Because then my virtual kid's got nothing. And John would not have anything. Okay, I'm charging. Good.
If he's so upset, he can go home and watch his videos.
He face around speaking to him.
All right.
Oh, yeah.
So the question says the suspended mass, it makes 30 oscillations in 15 seconds. Tell me, what is the period and what is the frequency of that motion? The what? How do you know that, Aiden? Aiden says lowercase f equals 2 hertz. How'd you know that? Are you going to tell me you saw it when I was up? Yeah, go figure. Okay.
Do the math.
All right, let's prove it. Yeah, do the math, right?
30 over 15 is doing still right.
Yeah, so frequency is how many cycles in 1 second. So wait, can we do that math?
If you have a recording going, they can't see you.
I know. I have to keep it plugged in. But what I'm doing is I'm taking 30 complete cycles divided by 15 seconds. Well, 30 divided by 15, again, cycles per second, gives me 2 cycles per second. Cycles per second is a hertz. It's how many cycles happen in 1 second. So that is our frequency. What about the period? 1/2, right? You could tell me, hey, the period is 1 divided by the frequency. It's the inverse. 1 over 2 is 1/2. What's my units? What are the units of period? Time. It'd be seconds in this case. The period is defined as the time it takes for 1 complete cycle or oscillation. Right? We feel okay about finding period and frequency? They're 100% related to each other. right? If you're given period in a question, you automatically know the frequency. And a lot of times they're going to do that to you. They're going to give you the wrong variable, and you have to use your understanding to find the correct variable to plug in whatever equation you need. That's super common, especially for these type of problems. But it's an easy fix, right? I'm going to stop there. What I'm going to do, I'll stop the slides. I'm going to hand out the notes, this notes packet that I found. I want to let you guys, the rest of class, kind of read through it. And there's a couple questions in there. I think we can answer most of them. There's like 3. And I want to try and give you guys some time to try it on your own, but then work through it together. Again, if you are a virtual student, I'm going to post this notes packet digitally for you, a PDF copy, so you have it. Again, there's a couple practice problems in it, but mainly it's to kind of supplement your notes and give you a really thorough summary of all the stuff I've talked about, kind of defining what is amplitude, what is period, frequency, blah, blah, blah. All right, so again, the rest of the class, I want you to take time to look over that. You've heard it before, I want you to review it, and then there's a couple practice problems throughout it. I want you to try to do those based on what we just did, and kind of that's all I want to do today.